Okay, everybody. In this series of videos, we're going to be going through another multiple choice practice test. Now, this is the released test from the 2014 international exam. So this is what the international students took in 2014. So we already have a video going over the 2015 international multiple choice practice exam. And now we're going to do the 2014. Now this is, in your practice test assignment, this is practice test number 4, multiple choice practice test 4. So if you've done practice test 4, then you've seen these questions already. So, if you want to go through the video looking at the different questions, then that's fine. But these questions won't be new to you if you do practice test number 4. Okay. So let's just jump right into it. So what I'm going to do is go through the test, and then as we go question by question, tell you what the answer is, and also kind of show you some of the notes that I took as I went through it. Some questions are pretty straightforward, so there's not much to it, and others, then we might take a little bit more time explaining. Okay, so again, let's just jump right into it. All right. So the first thing you want to note is kind of the structure of the test. A lot of times, there's only 1 or 2, maybe 3 questions per page. So you're gonna be going fast. Some questions are designed to take longer than others, right? You have this test only has 50 questions, but your test will have 60, and so you're looking at about a minute and a half per question. So you don't want to spend too long per question. All right, so let's just go right into it. So here it's giving us a list of different metallic oxides, ionic compounds with oxide of the ion. And notice the question is asking 1 gram of each of these would contain the greatest mass of oxygen. So it's asking which one is the greatest percent by mass of oxygen. And so right off the bat, I can see that it's going to be magnesium oxide, so B. But what we're doing here is I'm just doing... if you notice, each of the compounds has 1 oxygen, so I'm just doing what ratio is the biggest of oxygen to the entire thing. So 16 to 62, that was the molar mass of the N2O, 16 to 40, 16 to 94, and 16 to 56. So which one of these has the greatest ratio of oxygen by mass? And it's this one, so B for that one. All right. So here, it's giving us a list of characteristics. It's asking us what the solid could be. So notice we have kind of just a molecular solid, we have an ionic solid, we have a metallic solid, and then remember SiO2, a network covalent solid. So it has a high melting point, but not super high, so it's probably not silicon dioxide. It's not a network solid. It doesn't conduct electricity as a solid, so maybe you're thinking molecular solid, because if it did conduct electricity as a solid, you should be thinking metal. And then it does conduct when aqueous, so now that's your key that it's ionic, so the answer is B. Yeah, so those characteristics: high melting point, conducts when the particles can move, that's ionic. All right. So number 3, which of the following correctly identifies which has the first higher ionization energy? Has the higher first ionization energy, chlorine or argon, and supplies the best justification. So remember, we do include the noble gases for the electronegativity trend. If you look at the periodic table, argon is to the right of chlorine, so we know ionization energy increases going left to right. So argon has the greatest first ionization energy, and the reason that is because it just has 1 more proton in the nucleus. So let's find that. So we know the answer is not A or B. Argon, because it has a completely filled valence shell. No, that's not the reason. Argon, because it's higher effective nuclear charge. Yeah, it has more protons in the nucleus. So the answer is D. So just be careful about this one. Argon's stable because it has a full outer shell of electrons, but that's not why it's harder to remove one of its electrons. It's harder to remove one of its electrons because chlorine and argon have the same valence shell, energy level 3, but argon has a plus 18 nucleus and chlorine has a plus 17. So Coulomb's law, the higher the charge of the nucleus, the stronger the attraction. So there we go. All right. So question 4, notice a positive delta H. You immediately know that that means endothermic. Double arrow might be an equilibrium question. So a sealed rigid container contains all of these at equilibrium. Which of the following changes will increase the amount of Ba2? So we want to increase the amount of this. So which one of these things will cause a shift to the left? So if you remove O2, that would shift it to the right, so that's not going to do anything. Removing a small amount of BaO, remember, removing or adding a solid is not going to cause a shift. Adding helium, that's going to increase the pressure, but not increase the partial pressure of oxygen, so that won't cause a shift. Remember, adding an inert gas, so it's got to be D, but let's find out why. Lowering the temperature, if you remove heat, remember it's an endothermic reaction, so heat is a reactant, so if I remove heat, it's going to shift to the left to replace it, producing more of that solid. That's going to increase the mass of that, so the answer is D. Yeah. Okay. So again, we had to recognize that that meant endothermic, and so decreasing the temperature of an endothermic reaction will favor the reactants. All right. Number 5. Which of the following best helps explain why the value of delta H for dissolving calcium fluoride is in water is positive? So it's endothermic, and remember, an endothermic process, whether this is a physical change, but whether it be a chemical reaction or a physical reaction, endothermic means the attractive forces that are broken for the process are stronger than the attractive forces that get released that are formed by the products. So remember, we've talked about this multiple times. To dissolve, the ions have to break, so the ionic bond has to break. They have to separate from each other, and water molecules have to spread apart. So the forces of attraction that are breaking are the ion-ion bond between calcium and fluoride and a hydrogen bonding between water molecules. So those are probably pretty strong compared to the ion-dipole interactions that are formed. So we're looking for something like that. So calcium ions have a very strong ion-ion interaction with fluoride ions in the crystal, so that's probably the explanation there. Calcium ions have a strong ion dipole. That might be true, but the stronger the ion dipoles that are formed, the more exothermic it is, because this is an attractive forces that is formed in this process. So that's releasing energy. This is one of the attractive forces that are broken. So because this ion-ion interaction is really strong, it's going to require a lot of energy to separate those ions, which is leading to the fact that this is a positive delta H, an endothermic process. So the answer would be C for number 5. Okay. So if this had said this process had a negative delta H, then and why would that be? Then this would be a good explanation to why it might be exothermic. This is the answer to why it's endothermic. Okay. All right. Under which of the following conditions of temperature and pressure will H2 gas be expected to behave most ideal? So remember, ideal means so the two conditions that maximize a gas behaving ideally is high temperatures, low pressures. So you're looking for the highest temperature and the lowest pressure. So choice C. Least ideal would be the lowest temperature and the highest pressure. So choice B would be the least ideal conditions, and choice C would be the most ideal conditions. So ideal conditions, high temps, low pressure. Okay. This one I like because right when I look at it, I'm like, oh, okay, a piston, I'm changing the volume, and I know that volume and pressure are inversely proportional, so maybe you're thinking that this is a Boyle's Law question, P1 V1 equals P2 V2. They give you a P1, they give you a P2, they give you, they use that language, big paragraph, but none of that answers the question. Um, it says all of this, and notice right here it says temperature is held constant. It says, what effect do the volume and pressure changes have on the average kinetic energy? Nothing. It's just the fact that the temperature stayed constant, the average kinetic energy stays constant, so the answer is choice C. There you go. So 7, that's one of those where they're trying to distract you and make you think other things. Remember, same temperature, the temperature stays constant, average kinetic energy stays constant. They're directly proportional. Okay, that's it. Volume has nothing to do with it. Pressure has nothing to do with it. If you're asking about average kinetic energy, it's just about the temperature of the particles. That's it. Okay. All right, we'll keep going. Number 8. All right, so this one, I think this was on a concept check, one of your concept checks. So you're trying to figure out the formula for this compound. So you're trying to figure out what M is. So M could be sodium, potassium, copper, or lithium based on this data. So what they did was they gave you the mass of the filter paper and the mass of the filter paper plus the precipitate. So the first thing you have to do is do 2.23 minus 0.8. And remember, you do get a calculator now. So when this test was given, the students doing this problem didn't have a calculator, but now you have a calculator. So if you just do this minus that, that'll tell you the mass of the precipitate, which is AgCl. And that comes out to be 1.43, okay, grams. Well, if you take 1.43 and you divide it by the molar mass, you get 0.01 moles. So you have 0.01 moles of AgCl, okay? Which means, look at the subscript of chloride, that means you have 0.01 moles of chloride. So in this sample, you had 0.01 moles of chloride. But also think about it, it means you also had 0.01 moles of whatever metal M is, because the subscript for metal M is 1. So it's a 1-to-1 ratio. So we had 0.01 moles of chloride. Now, 0.01 moles times the molar mass of Cl is about 35 or 0.35 grams. So that means of the 0.74 grams, 0.35 of those grams was chlorine. So that means the rest of it, which would be 0.39 grams, is metal M. So 0.39 grams, and you had 0.01 moles. And to get the molar mass of something, you do grams divided by moles. So if we do 0.39 grams of metal M divided by 0.01 moles of metal M, we get 39 grams per mole. So which of these metals has a molar mass closer to 39? And it's potassium. If you go to the periodic table, potassium is 39.1. So the answer is B. Okay, so that's just stoichiometry. Okay, your favorite. Okay, so let's go to number 9. During the course of the experiment, so again, this whole paragraph is supposed to refer to questions 8 through 10. So during the course of the experiment, which of the following happens to the nitrate ions? Nitrate's just a spectator ion. So they remain dissolved in the filtrate solution. So D. Okay. And then again, remember, this information goes with question 10 as well. So remember, we're talking about a silver nitrate solution mixing with this solution. So if we look at the next question, it's asking what would the silver nitrate solution before the reaction? So remember, silver nitrate is dissolved in water there. So the silver and nitrate needs to be separated. So we know it's not choice D, because the ions have to be separated. So it could be A, B, or C. But remember, you also want the proper orientation of water molecules surrounding the ions, right? So this is a positive ion, so you want to make sure the oxygens are facing it, which is happening here. And this is a negative ion, so you want to make sure the hydrogens from the water are facing the negative ion. So this looks like the correct choice, but let's just double check. No, this has positive facing positive and negative facing positive, so that's not the right orientation. Same thing here, mixed. And then this has negative facing positive, which is right. That's the correct orientation around the silver ion. but this has negative facing negative, so that's the incorrect orientation around the nitrate ion. So this is choice A. Okay, so A was the correct answer there. Okay. All right, so moving on to number 11. All right, so we're mixing an amount of sodium hydroxide with an amount of HCl. So we don't care about the sodium, we don't care about the chloride. We're adding hydroxide to H plus, and they react in a 1-to-1 ratio to completion, strong acid, strong base. Even if it was a weak acid, it would go to completion. And we just have to know that hydroxide and H plus react in a 1-to-1 ratio. So if we do 0.2 times 2, that'll give us how many moles of hydroxide we started with. 0.5 times 1 would give me how many moles of H pluses I started with. And then big number minus small number would give me how much I have left over. So we have 0.5 moles of H plus, and we have 0.4 moles of hydroxide. So we're going to run out of hydroxide, and we're going to still have H plus, right? So what I would do is I have 0.1 moles of H plus left over, and the overall volume of the solution is 0.7 liters. So we have 0.1 over 0.7. So because you have a calculator, you could do the negative log of 0.1 over 0.7. It ends up being less than 1, so the best answer choice is this resulting solution is going to have a pH of 1, so it's choice A. But if you had to do this without a calculator, if you had 0.1 moles of H plus and the volume was 1 liter, then the pH would be 1. So now that the volume is less, and that means you have a higher concentration of H plus than 0.1. If you had a 0.1 molar solution of H plus, the pH would be 1. So if you have a higher concentration of H plus, it would be less than 1. So that's how you could tackle it without a calculator. But again, choice A right there. All right, so here we got first ionization energies. We got atomic radii. So the radius is decreasing, and ionization energy, first ionization energy is increasing. But we do notice that one exception there, right? Remember, we also have an exception from beryllium to boron, but they didn't include beryllium on the list. So remember, ionization energy increases as you go left to right, but notice that it actually gets less for the oxygen. So remember that exception. It's because the p sublevel of oxygen has a pair of electrons which increase the electron-electron repulsions within that sublevel. And remember, nitrogen's 3 electrons in the 2p sublevel are all unpaired, up, 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 whereas the oxygen's up, 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 down. So that's what we're looking for. Why is there a deviation from the first ionization energy trend? And it's because there is repulsion between paired electrons in oxygen's p orbitals. So that explains the exception there. Okay. So choice C. So let's see what notes I wrote here. Yeah, so remember, the 3 orbitals are, one of the orbitals is paired in the oxygen p sublevel, whereas all of the orbitals in the nitrogen are unpaired. So even though oxygen has 1 more proton in the nucleus, a higher effective nuclear charge, because of that added electron-electron repulsion there, it's actually a little bit easier to remove that electron than one of these electrons, right? Okay. So that's a flashback way from way back unit 1. All right, here we got which of the following equations represents the reaction that has a positive entropy change. So we're looking for probably more gas particles on the product side. So here we got less gas particles, so that would be a negative delta S. Less gas particles, again, even like gas particles to no gas particles, so that's even greater negative delta S than this one. We have a gas on this side, no gas on that side, so this would be a negative delta S, but notice we have a solid, just solid on this side, and then we end up with a solid and a gas, but we have a gas on this side. So this would be the positive delta S there. So 13 should be choice C. Yeah, C it was. Okay. So let's go to 14. Okay, the table below contains the information of the gases. So notice they're all at the same pressure. Now this one's a little bit less. But the key to note here, I think, is that sulfur's 32 and two oxygens is 32. So notice that the mass of the sample is basically the molar mass of this compound. So that means each compound has 1 mole of a gas here. That's why, because they have all the same pressures. They're at the same temperature in the same identical rigid containers, so the same volume. So that means they have the same number of moles. And this is telling us, hey, we got 1 mole of gas in each container. So on the basis of the data provided above, the gas in container 3 could be, so of these gases, which one is this? Well, it's which of these gases has a molar mass of 16? And it's methane. So choice A. Okay. Under the conditions given, consider containers 1, 2, and 4 only. The average speed of the gas particles is, it's going to be the greatest in the gas particles, which are the lightest. So greatest in container A, right? So same temperature means same average kinetic energy. Lighter particles are faster. So helium is the lighter of the particles here. So container 1 that contains the helium. Okay. And then 16, the best explanation for the lower pressure in the container 4. So why is it deviating from ideal behavior? So remember, you have two possible exceptions or reasons, justifications why something might have not behaving ideally, and it's because of either particle volume or IMS. So what would cause SO2 to not have as high of a pressure in the same size container with the same number of particles? It's not because the particle size is so much bigger than the others, because that would probably lend it to have a higher pressure in the same volume because the particle volume is significant. So it's not that, it's got to be the IMF. So SO2 is a bent molecule. It has dipole-dipole interactions, whereas the rest of these, methane, neon, helium, they're nonpolar. So it's got to be the intermolecular forces. So C. The stronger IMFs hold the SO2 together a little bit more in the sample, and that's why it's not colliding with the wall as much, and then it lowers the pressure a little bit. All right, so we'll go to number 6. Was that 16? Yeah, okay, that was 16. Let's go to 17. All right, so we've had this before. So this is just showing different diatomic elements. Remember how to interpret this. Down here would be the bond energy. So it's negative because that's the energy released when that bond is formed, but that would be the amount of energy required to break the bond. So whatever Y2 is, it has the strongest bond. And then up here is the distance, the bond length. So X2 has the shortest bond. So if it's hydrogen, nitrogen, and oxygen, we should know that nitrogen has the strongest bond because it's a triple bond. Oxygen's pretty strong because it's a double bond. Hydrogen's going to be pretty strong because it's the shortest bond. So I should know that X2 is hydrogen, Y2 is nitrogen, and Z2 would have to be oxygen. So the answer is A for 17. Okay, there we go. We got it. Okay. So let's go to 18. A 10-gram cube of copper at a temperature T is placed in an insulated cup containing 10 grams of water at a temperature of T2. If T1 is greater than T2, so the metal is going to transfer heat to the water, which of the following is true of the system when they attain thermal equilibrium? So they're going to meet in between a temperature somewhere between T2 and T1. We had equal grams of the substances, but notice that the copper has a much lower specific heat capacity compared to water. And you shouldn't be surprised by that. Metals tend to have lower heat capacities, specific heat capacities. So what does that mean? It means, remember, the amount of energy transferred is the same, but the copper is going to change in temperature a lot more than the water because it takes a lot more energy to change the temperature of the water. So the temperature of the copper changed more than the temperature of the water. That's true. The temperature of the water, no. The temperature of the water and the copper changed the same. No, the energy exchanged is the same. So it would be A. Yeah. Okay. So we'll finish up this page on this video. A solution containing HCl and a weak acid has a pH of 2.4. Enough KOH is added to increase the pH all the way. So we've neutralized all of the acid, all the H+. the amount of which of these species increases as the KOH is added. So remember, the HCl is already dissociated, right? So you're not going to increase the amount of chloride because the amount of chloride in the solution initially is the amount of HCl that you added because it completely dissociates. You will gain chlorite, ClO2 minus, because this is a weak acid, it stays together. So as you add the OH minus and it takes away all this H plus, once all that H plus is gone, the OH minus will then take this H plus away, and then you'll start increasing the amount of that ion there. So the answer is C. And it's because weak acids stay together, strong acids dissociate. Okay. And then here we have the auto-ionization of water. Now they gave us the pKw. Now, understand what you would be doing here is to get the kW is 10 raised to the negative this. So kW is increasing. So as pKw decreases, kW is increasing. Kind of like how as pH decreases, the amount of H plus increases, right? So that's the same thing with kW and pKw. So they're telling you this reaction becomes more favored at higher temperatures. So at higher temperatures, you get more hydronium. So based on the information above, which of the following statements is true? As temperature increases, the pH of pure water decreases. Remember, we got to be careful about this. You're getting more hydronium, which means it's more acidic, which means pH decreases. So the answer is D. A lot of kids will have the right kind of idea, but they'll accidentally pick C because they'll just think pH increases means more acidic. No, pH decreases means more acidic. We're increasing the amount of hydronium, which is decreasing the pH as temperature rises. So hot water is more acidic than lukewarm water. So that's one, make sure you're pumping the brakes and going, okay, yeah, I'm increasing the amount of hydronium, which means I'm making it more acidic, which means the pH is decreasing. Okay. All right, so that's part one. We'll go over the rest in another video. Hope you're enjoying it.